Okay, cool. So let's go and actually put this in ease, and I'll show you how to do this in ease real quick. All right, so we have our problem information, W equals 1, H equals 1, whatever we could pick, whatever we want those to be. I'm going to define two coordinates. So we'll define X and Y in terms of X bar and Y bar. So X bar would be just the position X divided by the total width. So like a fractional coordinate. And then here, this is actually implementing the solution. So I'm going to create a duplicate loop, right? We're going to compute the unknown constant for every I that we choose. Obviously, we can't go to infinity in ease. So we're going to pick some number, right? And I'll show you how this kind of plays out. We'll pick 11 for now. So what we're doing is we're going to evaluate 11 temperature terms and then sum them back together. Right, so here's our unknown constants. We just evaluate that based on before. We program in our lambdas, evaluate that. And then here's our temperatures. We're duplicating for all those 1 to 11 temperatures, exactly the solution that we came up with. So I mean, it's really amazing how simple this is based on all the stuff we just went through. It's a really elegant solution. And then in the end, you just sum everything back together using a function like this. We're summing all of our t from I equals 1 to n that we computed up here. We're summing that all back together, and that gives us our t. All right, and for now, I'm going to evaluate this at the midpoint of this domain, 0.5, 0.5. Okay, so solve this. And then a few things to look at. So let's look at the solution. This is the arrays window. So Ti, right? Ti is the temperature contribution from each of the terms that we have. So you can see the first term is a really important temperature contribution. As you go up in order, as you go up in the sequence of i's, it becomes less and less important. So really, we probably could have got a very accurate estimate of temperature after what? I equals 4 in this case. But this does depend very strongly on the position in the domain. Okay. Because we're calculating CI based on the position. Okay, so let's, okay, so this is what we have. Let's actually look at the solution. So let's start here. So this is a contour plot of temperature. We had our adiabatic condition on the right and on the bottom. On the top and on the left, we had fixed temperatures. So you can see that, yeah, this is really a 2D problem. There's a huge amount of heat transfer that's happening, like right up here, right? Because you have basically a discontinuity, which is what you were talking about last time. But we have this solution, right? Let's look at a little bit about how the solution depends on the number we're choosing here. So let's say I want to evaluate this at this discontinuity. Right, so right at maybe x equals 0 and close to y equals 1, right? That's up in that upper left-hand corner. So if I solve this now and look at my solution, we have a problem, right? I've evaluated out to 11 terms, and I'm getting pretty much equal contributions from each of the temperature terms that I'm solving for, right? So that's not good. I've truncated my solution to a point of inaccuracy. So I would need to go back here and say, well, okay, actually, I want to look at maybe 101 terms and solve this again. Okay, let's see how we do. So we scroll down. All right, it's at 101, still not good enough. Okay, I'm still adding significant contributions. So let's try one more, and then show you one more result, and then we'll wrap up. Okay, so let's do 1001. Takes a bit of time, and let's scroll to the bottom. Okay, with 1001, by the time I'm getting out to say, well, I don't know, 500 or so, I'm pretty good. Right? So I could, with good accuracy, have a 2D solution for this problem with maybe n equals 500. Okay. The last thing to look at is, just in the last few seconds here, is I want to look at this plot. So this plot is showing us as a function of dimensionless position, x over w, for different values of dimensionless y, what my temperature profile is. So right away, you're drawn up here, but let's first look down here. So at y over h equals 0, this is the temperature at the base of the thing of the domain, right? And as you move up, you get this temperature profile. So what's happening right at the top? That's kind of the interesting part. Well, right at the top, we have the discontinuity. So you're having to sum together a bunch of sines and cosines with different frequencies to match that profile at that boundary condition. If you don't have enough terms, you're really going to struggle. So you can see with 11 terms, it really kind of oscillates significantly. With one term, with 21 terms, it does a little better. 101 terms, even better. But you're never going to get an exact match at that corner because it's a physically impossible situation. Okay. But this solution is really good in other parts of the domain, and so that's kind of where you'd want to use it. Okay, let's wrap it up there. Thanks.